All right. I have to start with a caveat. Mung asked me to talk about search algorithms, and I sort of interpreted that fairly broadly, and I changed the topic somewhat. So what I'm really going to talk about is how we do things with very large data sets very efficiently. And this is something that's very closely linked to searching at web scale, the kinds of algorithms that Google and other search engines have to deploy in order to be able to do anything at all with just the large volumes of data that they have to deal with. But at the same time, it's not, there are lots of special topics we could go into about search itself, as Mung alluded to in his lecture. And there are many things that he attributed to what I would cover in the 30 minutes I have, but I'm afraid I'm not going to be able to cover them. So I'm happy to answer these questions later, perhaps, if you'd like. But I just want to warn you, there's a little bit of a diversion, but a relevant diversion, I hope. Okay? So I want to start with talking about some problems that people face when they're trying to deal with very large data sets. And having discussed those problems, I'll talk about new ways of thinking that have evolved to design algorithms to deal with them. And then finally we'll come up with some, I'll describe some building blocks of the algorithmic toolkit to design algorithms for very large data sets. I recognize a few faces in the audience. Those of you who've taken 340 last year, some of this might be a repeat of things you've seen before. And for those of you who haven't taken 340, those who are currently in 340, it's a little bit of a preview of something that you might see later on in the course. Okay, so let me start with a very simple problem. Suppose you're given a list. How do you count how many distinct elements are in this list? Any ideas? This is supposed to be an easy question. It's not a trick question.
You count them?
Yeah?
You count them?
Yes, how do you count them?
1, 2, 3.
No. How do you know that okay, so the list could have repeats, right? And you don't want to count the repeats. How do you eliminate the repeats? Yeah.
I mean, you could go through each element in the list and maintain a symbol table or something, and you just keep putting elements, and if it's a repeat, you just discount it.
Exactly. Okay. You want to say something? You can sort them and then just go through the sorted list. So either of these solutions would work. And of course, it's a very simple problem, one that you might encounter in a very first algorithms course. Standard solution is to use a hash table. You could also use sorting, right? Hash table is just the same thing as a symbol table. As you encounter elements, put them into the hash table, and obviously if you encounter a duplicate, you realize this. Okay, so this is a very simple problem. What makes this problem very hard is what happens if the list was very big? What if you had to do this not on 1,000 elements, but 1 billion elements or 1 trillion elements? Okay, then all of a sudden, all of these simple approaches, like using a hash table or doing sorting or whatever, go out of the window. Well, number one, you'll need a whole lot of memory to actually keep a hash table. And of course, modern computers are capable of doing hash tables even of this size, perhaps. But at this size, we're sort of at sea. Okay. Sorting again, sorting such a huge list takes a very long time. Okay. So why would you care about a problem like this? Well, if you think about Google, for example, some statistics that they released earlier this year say that Google in its entire lifetime has seen something like 30 trillion URLs. They crawl something like 20 billion pages a day, and they serve about 3 billion searches a day, which means 100 billion searches a month. Okay, so that's the scale at which they're operating. And if you had to solve the simplest kinds of, if you had to answer the simplest kinds of questions about what they do, like how many queries did they get in a day, how many distinct queries did they get in a day, how many distinct queries did they get in a month or a year, you're faced with solving what seems to be a very simple problem, but is very difficult just because of the immense scale at which you need to operate. Okay. Of course, answering this question of how many distinct queries you have is a very simple statistic that you might want to compute and keep track of as time goes by. But you might want more sophisticated statistics like how much did the queries change from day to day? How much are they different today compared to yesterday? How much are they different this month compared to the previous month? This month compared to the same month last year, and so on and so forth. And all of these very, very simple questions just seem incredibly difficult when you're dealing with the sizes of data that Google deals with. Okay? There are other settings where you have lots of data and you'd like to be able to come up with algorithms to do simple things. A network router is one example. It sees a lot of packets whizzing by at fast speed. Current home routers are even capable of speeds about 1 gigabit a second. Commercial routers are capable of speeds of something like 10 gigabits per second. The router is something that's a really simple computing device. All it does is receive packets and forward them along. It could perhaps do some very simple sort of analysis on the data that it's seeing. How could you use this very, very simple computing device to do simple monitoring like, can you tell me how many active flows are in the router? Which are the flows that are contributing most of the traffic? And these things are important because monitoring these sorts of things are central to various security measures like early detection of denial of service attacks. Okay, it's important to keep track of what's going on, what sort of traffic you're seeing, because changes in this might signal that something strange is happening, and you might want to take some security measures. Okay, so very, very simple statistics like this are a huge challenge just because of the amount of data that this router is seeing and the fact that the router itself is a very, very simple device. Okay, so in general, there's this talk of big data everywhere. If you read the news, read magazines, every other day there's an article about how we're surrounded with data. We need to find ways to make sense of the data. And what I'm really going to talk about is, what are some of the algorithmic techniques that we can do to tame these, we can use to tame these big data problems. Okay. All right. So that's the introduction of what the problems are. Let me talk about what models we could envision to design algorithms with this. Clearly, our traditional notion of having all of the data available to us, having the algorithm that has random access to the data, fitting all the data in memory, all of this doesn't really apply when we're dealing with data at such large scale. So, the two operatives are, number one, the data size is very large. It far exceeds the available memory, and that's just a reality we have to face. We can't actually store all the data in memory. And the other thing is that there's a new emphasis on efficiency. Usually when you design algorithms, polynomial time algorithms are considered efficient and implementable, but in reality, when you're dealing with data sizes of this scale, you want algorithms that run in linear or near linear time, perhaps. Even something like quadratic at the scales of which we talked about are impractical. Okay, so that's what those are sort of the parameters. Okay, so one kind of model that's used, and we'll see later on in the lecture, is the idea of taking our large data set and somehow reducing it to a smaller size. Okay, so turns out that we can do this in many cases. Replace the original data by some kind of compact summary, such that by discarding the original data and just looking at this compact summary, we can actually solve, or we can actually answer the questions that we care about. That would be wonderful if you could do this, because you've effectively reduced the data size. It turns out that in many cases this is actually possible. Okay. Now, one thing you have to give up on is the idea that you really want to solve a problem exactly. In most cases, like if you want to find out how many distinct elements were there in the queries, you really care about whether I give you a 1% approximate answer or whether I give you the exact answer. It doesn't really matter. So in most cases of interest, it's okay to not give the exact answer, but give something that's fairly accurate. And turns out that this relaxation, moving from getting the exact answer to tolerating some error, bounded error, is something that actually makes many problems tractable. Okay, so we'll see some examples of this idea. Another idea that's been very useful is a certain model called the streaming model. And the streaming model is the following. It says, you have to design your algorithms that operates in the following way. Imagine the data as being one stream, and you make one pass over the data, or perhaps a few passes over the data, but you can remember only a small amount of information relative to the size of the data, right? So you can afford to remember very little, and you're only allowed to see the data in one pass or in several passes. So for example, you can't really zigzag back and forth. You don't have random access to the data. Okay? And the point is, if you could actually design an algorithm that works in this very, very restricted way, you could actually run it on very large data sets very efficiently. Okay? So it seems like we're really, really tying our hands and putting a blindfold on how could we possibly do anything in this very, very restricted mode of operation. But turns out that there are very interesting things that you can do even when you restrict yourself to interacting with this data in this very controlled way. Just a little bit of history of where this notion of streaming algorithms came from. Actually, this idea of trying to design algorithms that work in one pass of the data, remembering very little, predates the internet even, or big data sets and so on. It was really sort of a fun problem that people worked on. In fact, there's some work by Flageolet and Martin that exactly deals with this problem of estimating distinct elements, and we're actually going to see what was the idea that they came up with, because it's actually relevant today to the scale of for the data sizes that we actually face with today. Another piece of work back in 1980 was by Munro and Patterson, and they looked at the problem of how much space do you need in order to compute the median. So you have a data set of size n, you have only a small amount of space, you can make a few passes of the data. If you're allowed k passes, how much space do you need to actually compute the median? And they found out a very sort of tight answer for this question. It turns out that if you're allowed to make k passes, you can do it using something like n to the 1 over k space. Okay, and these algorithms, as I said, were developed very, very early on, even before this model was really formalized. This model was really formalized by work of Alon, Matthias, and Szegedy in '96. And this is sort of a landmark paper because it really sort of formalized this model. It talked about what you can and cannot do in this model, gave examples of how to prove negative results. And for this work, they won the Gödel Prize in 2005, which is a very prestigious prize in computer science. Okay, so let me also mention, some of you might have seen or heard about MapReduce. That's another model of interacting with very large data sets, something that was proposed by Google, in fact, and it is the basis for a bunch of practical implementations of distributed algorithms. There is something called Hadoop that some of you might have heard of. All this is sort of relevant to the discussion of how to deal with large data sets very efficiently, but unfortunately, I'm not going to have time to talk about all of these things. Okay, so next, in the rest of the lecture, I just want to give you a glimpse of some of the ideas, the algorithm, the ingredients of the algorithms to deal with large data sets. Okay, so I gave you a bunch of problems. I told you how we might interact with data sets in order to solve these problems. Now I want to tell you, okay, now that we've tied our hands, if we want to solve this problem of very large data sets, how do we actually do this? Okay, so I talked about data reduction, the idea of taking a data set and sort of reducing the size of the data set. Actually, if you think about it, this is a concept that we know and are very, very familiar with in our lives. If you were to ask the question, what fraction of voters today prefer Obama over Romney? Very relevant question, a lot of people care about, but very difficult to answer this question if you really want to know what the exact fraction is, right? You have to ask every single voter, well, what do you think, what do you prefer? It takes a lot of time and effort to actually get the exact answer, and we really do this once in every 4 years for a good reason. But on the other hand, this is something that people actually make predictions about every day. Every day you look at the newspaper and you get some estimate of what's the approval rating of Obama today, what's approval rating yesterday, how many, and various other questions that you might think about. So this is something that we solve or is routinely solved every day by sampling. Okay, we don't actually ask everybody what their opinion is, but the point is that if you actually pick a random set of people and you ask them what is your opinion, that the percentage that you compute on the random sample is actually a very good estimate of the actual percentage on the entire population. Okay, that's George Gallup, and all of you have read about Gallup polls. This is something done by the Gallup organization that he set up. Okay, so let's think about sampling. What does sampling do? What does sampling do? The idea is, if you pick a random voter and you ask them, do you prefer Obama? Then the probability that this random voter says yes is just a fraction of voters who prefer Obama, right? It's a basic fact. Do we agree on this? Okay, all right, it's a very simple thing. But this is actually very useful. Why? Because now, if you pick several random voters and independently ask them the same question, then the estimate that you get from this random sample is actually a very good estimate of the actual fraction. Okay, that's the basis for polling. That's the basis for random sampling. Okay, so let's sort of take a step back and think about what this actually did. The idea is that you produce a random variable which has the correct expectation. Okay, in this case, the expectation is the fraction of voters who prefer Obama. This is the quantity that we actually want to estimate. So you design a random variable that has the correct expectation. You take many copies, independent samples of this random variable, and you average. Right? Because this random variable has the right expectation, once you take many copies, the expectation of the average is exactly what you want. But the point is that by taking many copies and averaging, you get tight concentration. Okay? Now, in reality, if you really want to analyze this, you need to think about what's the variance of the random variable, what's the confidence bounds that you want on your estimate, so on and so forth. This is a topic for probability, which some of you may have seen, some of you may not. I'm not going to go into this, but believe me that once you design a variable with the right expectation, with a little more calculations, you can sort of determine what sort of sample size you need in order to get confidence bounds and so on and so forth. Okay, so I'm only going to focus on, for all the problems we care about, we're going to try to design random variables that have the right expectation. Okay, and further, the important thing is that these random variables will be computable very, very efficiently by making just one pass over the data. Okay, that's the key idea that we're going to apply. All right, so having said that, let's go back to our question of distinct elements. It turns out that the solution that Flageolet and Martin came up with is tied to a simple puzzle. Okay, so let me tell you what the puzzle is. I know some of you probably know the answer to this question. If you haven't seen this before, I encourage you to think about it. So here's the experiment. Okay, so let's say you have the interval 0, 1, and you throw k random darts inside this interval. So you pick k random points in the interval 0, 1. Okay? Everyone, experiment clear? Okay, so the question is, what's the expected value of the minimum of these k elements? Any guesses? If you had to guess, what should the minimum be?
0. 100k.
Okay, so 0 seems a little extreme because for it to be 0, you want some element to land up here. What I'd like to know is what is it as a function of k? And you're right that in some sense as k gets larger and larger, this minimum is going to get closer and closer to 0. But I want to understand what behavior it is. 1 over k is actually a very good guess. 1 over k plus 1 is actually a better guess. So okay, how do you justify 1 over k or 1 over k plus 1?
1 because probability of each of k plus 1 being the lowest is that. And that's also the same as the probability of it being lower than the lowest third right now.
Okay, but how does that help you compute the expected value of the minimum?
Because then you know that the probability of it landing lower than the lowest third right now is 1 over k plus 1. So then the expected value of the expected length of that segment is 1 over k plus 1.
I think you're suggesting a very slick proof which escaped me at this moment. And I have to say, when you stand in front of the class, your IQ usually drops by 50%. So I think you're probably right, but maybe we should talk about this after class. Okay. So it turns out the right answer is indeed 1 over k plus 1, and we might have a very clever proof of that here. If you didn't know that the answer, what the answer should be, the way I usually think about this problem is, well, it's kind of reasonable to assume that these k elements are sort of uniformly spread in the interval 0, 1. Okay? And if that's really the case, if we believe this, then each of these gaps should be 1 over k plus 1. There are k gaps. So in fact, the smallest element should be 1 over k plus 1. Okay, this is very crude. It's by no means the correct answer. But if you had to guess, 1 over k or 1 over k plus 1 is a reasonable guess. And if you actually do the calculations, it turns out that it is indeed 1 over k plus 1. All right, good. So if you have the minimum of k random numbers in 0, 1, the expected value is 1 over k plus 1. Why is this actually important to the question that we started out with? The question was, how do you estimate how many distinct elements there are in your data stream? How could you use this fact to estimate the number of distinct elements? Yeah?
You could use that to guess the minimum and then remove that from the sample and guess the minimum of the remaining ones. And then that would give you, I lost my train of thought.
Okay.
And the minimum and then the k plus 1 to estimate how many there are.
Okay, so I think I know what you're saying. How about this? Imagine computing a hash value for every element, and this hash value is a number between 0 and 1. So think of our hash function as a random function, so it assigns every element a number between 0 and 1 at random. And we keep track of the minimum as we go along. Okay? If you see many copies of the same element, the hash function is always going to map onto the same value. The minimum doesn't change, right? So what is the minimum really? The minimum is just the same, the distribution of the minimum is just the minimum of k random values in 0, 1. So the expected value of the minimum is 1 over k plus 1. Great, we're done. If you actually wanted to get a good estimate of the number of distinct elements, you would compute not one hash function, but maybe 100 hash functions or 1,000 hash functions. Keep track of the minimum of all of them. Okay, and the end average. And you get a very good estimate of 1 over k plus 1, where k is the number of distinct elements. Invert this and you have a very good estimate of the number of distinct elements. Okay? So it's a really beautiful trick, originally discovered by Flageolet and Martin, and it's amazing how it completely bypasses the need to store any sort of hash function, do any sort of sorting, and comes up with a very good estimate of the number of distinct elements. Okay? All right. Next I want to talk a little bit, actually I don't have very much time, so I'm going to have to breeze through this section. A class of methods that are used to figure out, in a very large collection of documents, which documents are similar. Okay, and this is actually an important problem because, number one, when a web search engine crawler goes out, it brings in a bunch of documents. There are many duplicates or near duplicates, and you want to get rid of these guys. There's no point Google returning 100 results which are almost the same. It wants to, it wants to return results that are distinct, and ideally actually not even store these almost similar documents. So that's number one. And secondly, in addition to not storing them, sometimes at query time you might want to figure out that the results that you're actually returning to the user are almost the same, and you might want to suppress these things that are almost the same. And if you've searched on Google, you might often see, there are so many results that are very similar to the ones we've shown to you, and we suppress them. If you'd like to see them, then click here, right? So there are various reasons why you'd like to eliminate near duplicate documents. Now, this is sort of a difficult question. How do you find and eliminate near duplicate documents? And I'm going to describe a scheme that was originally developed by Andre Broder and his collaborators in the context of a search engine called Alta Vista, which in the old days predated Google and was the leading search engine at the time. Now, I'd be surprised if very many of you know about Alta Vista at all. So let me sort of very quickly describe the main idea behind this. It was a very, very cute idea. First I have to tell you, how do you define similarity of documents, right? What does it mean for two documents to be similar? There are many ways of doing this. One way is the following. You take your document, it's the Declaration of Independence, and you slide a window of 3 words across the document and look at all the 3-word sequences that you encounter. And doing this, that's your set. So now I've taken a document and I've produced a set. Henceforth, I'll think of the set as representative of the document. Having produced sets, I can now define similarity of 2 sets, and I'll use that as a measure of similarity of the original documents. One reasonable measure of similarity of the documents is the following. Look at how much they overlap. Look at the size of the intersection relative to the size of the union. Okay? So henceforth, let's agree that this is the measure of similarity that we'll use. Okay? If 2 documents were identical, the sets that they produce would be identical, so similarity would be 1. And we're going to work with the hypothesis that similarity is a reasonable measure. Similarity defined this way is a reasonable measure of how similar 2 documents are. Okay? So here's the question, right? Can you produce a sketch, a very short summary of a document, a set in this case, such that you can estimate the similarity just by looking at these 2 sketches instead of actually looking at the original document? So clearly I can look at the full text of the document, compare them, and say how similar they are. But that would be too slow and not acceptable. So can I get rid of the original documents, replace them all by short sketches, and estimate the similarity just by looking at these short sketches? This is something that you could actually hope to do at runtime, right? If you actually had to go and look at the original documents at runtime, not a good idea. All right. The first thing that might come to mind is something called random sum. Right? You might say, well, how about storing a random subset of elements? This just does not work. Okay? If you had 2 sets with 10,000 elements, let's say, identical, what's the problem? If you look at a random sample from set A and a random sample from set B, say you sample 100 elements, the expected intersection of these 2 samples is 1. Right? It gives you no information whatsoever that these 2 sets are identical. So random sampling per se doesn't work. Okay? But here's a little variant of random sampling that actually works. Okay? And it's actually very, very cute, and it's related in some sense to what we did before. So here's the idea. You apply a random hash function to every element of the universe. Okay, so you have a random hash function. You apply it to every element of the set, and you just remember the minimum. Okay? Let's assume that we have no collisions. So we have a hash function that has no collisions. And here's the claim. The claim is that the probability that the minimum of A is equal to the minimum of B is just the similarity of A and B. Okay? So it's actually not very hard to show this. Maybe I'll leave this as an exercise. The claim again is the following. You have 2 sets A and B. Let's say you apply a hash function to every element in the universe. You look at the minimum over A, the minimum over B, assuming that there are no collisions. What's the probability that the minimum over A is equal to minimum over B? The claim is that this probability is exactly this. Okay? So great. We were able to design a random variable that has exactly this expectation to get get a high confidence estimate. You would do this not with 1 hash function, but with 100 hash functions. And for every set, you would store a sketch consisting of the minimum with 100 such hash functions. Okay? And now you can use these sketches to actually get a very good estimate of similarity. All right. I had hoped to talk about a lot more, which I will skip. But maybe I'll give the slides to Mung and he can post them. This is another scheme to estimate similarity that I actually worked on when I was at Google. I'm not going to be able to tell you about it, but you can look at the slides a little later. I just wanted to say that many of these techniques are really useful beyond the problems that we talked about. The idea of random projections, which we didn't quite discuss, is really useful in dealing with very large data sets. It's a very useful technique to reduce data sizes. Nearest neighbor search data structures are very useful in searching large, complex, high-dimensional data sets. And designing hash functions like the ones that we saw for set similarity are actually the building blocks of designing very, very efficient data structures to do these search problems. There's a little issue with randomness. We sort of assume that everything is completely random. You have a completely random hash function. Turns out in practice it's not really true. There's a way to fix this, which I'm afraid we won't be able to discuss. And so in conclusion, I just want to say that there are a lot of cool ideas, theoretical ideas, which are very practical in design, that are useful for designing algorithms that work with very large data sets. I want to give you a glimpse of this algorithmic toolkit. It was a shorter glimpse than I had thought I would do. But there are many interesting problems here. I hope I will motivate some of you to think about them.